Thanks, Tom. It's nice to be here. So this will be actually a bit different talk because I'm not the main author of what I'm showing, but yeah, the people involved are listed here. Well, let me just start with a brief introduction. This was developed at ETS Institute in Gliwice, Poland, by, well, a bunch of people, most notably Piotr, who's my current boss. And those are actually not physicists. They are actually like IT guys. So I hope they know what they're doing, definitely more than I do. And there's a number of libraries, as you can see, Cumulants, Cumulants features and updates, and I'll talk briefly about those. And here are the references. And well, for me, I'm actually a Julia newbie myself, but really excited to finally dive into it after being forced to like stick to Python to get my PhD actually finished. Right. So what are Cumulants? Well, I know about you, but if I hear the word, it doesn't ring a bell instantly for me. But when somebody says, well, standard deviation, mean, kurtosis, then it does. So, and well, those are basically examples of cumulants of the first orders. Well, I guess the Taylor expansion should also ring a bell, of course, and this is basically how you get them. Those are basically those KD coefficients when you expand this generating function. And this, well, to get them, you differentiate the whole thing and take the value at 0, which well, comes in handy when you have things like automatic differentiation, for example. And yeah, this can be useful in a number of analyses. Well, let me jump to the results of the first work, which was to basically develop an algorithm which basically computes this for, well, rather large tensors. So on the x-axis, what I'm showing here is the number of variables for which I do it. So basically number of our dimensions. And we have the speedup. And speedup is computed with respect to this so-called naive approach, which would be, so the improvement in this code is mainly in how you store the data, because those tensors that you get are often symmetric or even supersymmetric. This has nothing to do with supersymmetry in theoretical physics. This is ultra confusing, I know. But yeah, this means basically that you don't need to store a lot of elements actually to retain the whole information. So yeah, you can see that we get speedups up to like 2 orders of magnitude with respect to the naive approach. That theoretical expectation is only like factor 24 for this case, which is the 4th order cumulant. But well, apparently itself had some extra bonus in performance apart from the expectation just from the algorithm itself. And here is also a comparison what you can further improve. So this is comparing, this is again a speed up plot, but now we compare what if we do parallel processing. So this starts with 1 because now we compare with the basically single processing from the previous result. And here we can improve by another factor of, well, roughly 5, depends on the number of processes. So it's not fully parallelizable. As you can see, at some point we start to actually get worse because some things, well, cannot really be done at the same time, but still gives you some advantage. And we also, the authors also did a comparison with the state of the art, which is a library written in R. And what was done here is again a speed up plot, so and also a function of the dimensions. There's also some funny t, which is the number of samples. And yeah, here we just compare again the algorithm against, but this time not against the naive approach, but against the state of the art, which was published in, well, you can go to the Indico and click the link in the slide in that paper. And this was re-implemented first in Julia on the left and in R on the right. So, well, in Julia, when you re-implement the the state-of-the-art algorithm in Julia, you actually get higher speed up, which means that, well, the algorithm was really optimized for R, because, well, then the difference when you move to the one in Cumulants.jl is less. But still, I mean, factor 140 is, or, well, whatever, even hundreds is definitely a nice advantage. But that's not all you can improve there. Another thing, when you, for example, want to do some online recall, for example, is that you may have data coming in chunks, or you may even have like offline work, but you just want to really improve further in speed. So what you can do, you can also slice your data and just pass it in chunks to the algorithm. So this is handled by CumulantsUpdates.jl, and this provides you further speed up, as you can see. So this is with respect to the standard Cumulants.jl without slicing the data. And on the x-axis this time it's a function of the batch size basically. So the smaller chunks you get, you can get speed ups up to like factor 20. So that's also useful. And you may wonder, okay, where do I use it? There actually were already a number of use cases. So not directly of this algorithm, but those are some analyses which generally make use of higher order cumulants. So at LHC there are a few analyses, also Astro things. Well, it's also quite popular in lattice QCD. And yeah, here it's something maybe I didn't stress before, but those analyses often use cumulants of orders higher than 4. Why it's important? So for example, if you consider the state of the art, which I mentioned here, this has a specialized algorithm which is a bit faster, but it only goes up to 4th order. So you're limited. But with the Cumulants.jl, you can basically compute at any order, and you are always faster. So that's nice. And I checked those analyses actually do go up to like 8th order in some cases. For example, in this lattice QCD things. So yeah, if you need to compute them fast, that's the way to go. There's some other stuff. Well, I'm just mentioning because it's from the same authors. There are other projects. It's not really HAP anymore. So, but if you're into quantum computing, you may also wanna check out the quantum information library, which provides you basically a complete set of functions for computing your states. It natively works with bracket notation, so you can very conveniently compute your stuff through this library. So if you are doing stuff more into the quantum side, definitely check that out. And there's also another smaller one for generating random matrices on GPUs. All right, yeah, so that would be it. It's rather short one. So yeah, if you need some fast Cumulant computation, definitely check out Cumulants.jl or the papers. You can also contact me and or directly the authors if you want to learn more. Yeah, I use this also to make some advertisement inside an advertisement about some my ideas for project which I'm thinking about starting. So that's something to maybe also spark some discussion in the coffee break. I didn't really talk about what, for example, Corsica is, but it's basically a code to simulate cosmic ray interactions. And my background is mostly actually Monte Carlo simulations. So what I'm thinking about is, for example, a project where we develop something alternative to Corsica, but in Julia. I'm aware, of course, that there is Corsica 8 ongoing, but well, perhaps it can be done more efficient and hopefully also just easier to write. Well, this never hurts to have something to compare Corsica against, because so far it's actually the only thing you have really from serious Monte Carlos. The other thing I was thinking about is simulation of acoustic signals, which could be coupled to this. There's a known mechanism. There are some simulations. To my knowledge, none is published or like open source available to others, which is a shame. And I think we could try to change that. Yeah, so that's it for me. Thank you.